In my earlier video, I had discussed about Jordan canonical form. I had seen two linear map A and B, which is defined from x to x, are similar if they have same Jordan canonical form. If you don't see my previous video, at first I will highly recommend you please see my previous video. Then today's video would be so easy. Today's goal of this lecture is, today I will see how to evaluate Jordan canonical form of a matrix easily by minimal polynomial. By minimal polynomial, we can evaluate Jordan canonical form of a matrix very easily. And if we can to find Jordan canonical form of two matrix, then we can to tell easily two matrices are similar to each other. Our next goal is, I will say, generalized eigenvector. When a matrix similar to diagonal matrix, or when a matrix be diagonalizable, that means this is similar to diagonal matrix, then all eigenvector corresponding to eigenvalue are always linearly independent, we all of us know. But otherwise, when the matrix be not diagonalizable, that means all eigenvector corresponding to eigenvalue not be linearly independent. Then I will see these eigenvector be the generalized eigenvector. And today's goal of this lecture, I will see what is the actual generalized eigenvector. Okay? So, at first I will highly recommend you, please pay attention to this video, because Jordan canonical form, this concept is an important concept for higher study. Okay? Let's see how we can evaluate Jordan canonical form of a matrix by minimal polynomial. Our question is how to find the Jordan canonical form by minimal polynomial. For this, given n cross n matrix A in Jordan canonical form, we all of us know the eigenvalues are actually the entries on the main diagonal. Second, if the characteristic polynomial is lambda minus lambda 1 to the power r1, lambda minus lambda 2 to the power r2 up to lambda minus lambda k to the power rk, where this ri is the number of occurrence of lambda I on the main diagonal, and minimal polynomial is which is denoted as ma lambda equal to lambda minus lambda 1 to the power s1, lambda minus lambda 2 to the power s2 up to lambda minus lambda k to the power sk, where obviously this si is the size of largest block corresponding to the eigenvalue lambda I in the matrix A. That means by minimal polynomial, we can tell the size of largest block of the Jordan canonical form corresponding to any eigenvalue. Are you getting? Oh well. We all of us know the geometric multiplicity of lambda I is actually the number of lambda I, means Jordan block in the matrix A. Consider a 6 cross 6 matrix having characteristic polynomial PL lambda equal to lambda minus 3 to the power 4 times lambda minus 2 whole square, and the minimal polynomial which is denoted as ma lambda is equal to lambda minus 3 whole cube times lambda minus 2 whole square. For this, Find the Jordan canonical from A. Algebraic multiplicity of lambda equal to 3 is 4 and algebraic multiplicity of lambda equal to 2 is 2 and order of minimal polynomial degree is 3. Therefore, 4 equal to 3 plus 1. That means there exists one block of order 3 and another block is 1. And since order of minimal polynomial of eigenvalue lambda equal to 2 is 2, therefore obviously 2 equal to 2. Therefore the Jordan canonical form would be noticed for lambda equal to 3 there exists 3 block and 1 block. This is 3 block and this is 1 block. And lambda equal to 2 there exists 2 block. Are you getting? And this is 6 cross 6 matrix. Therefore, this is the Jordan canonical form of the matrix A, whose characteristic polynomial is this equation and minimal polynomial is this equation. Are you getting? How by minimal polynomial we can easily find Jordan canonical form? I will see one example. Consider the characteristic polynomial of a matrix which is equal to x plus 4 to the power 5 times x minus 1 whole cube and minimal polynomial of the matrix is x plus 4 whole square times x minus 1. Then the question is possible Jordan canonical form. And here very interesting thing, I will solve this math by partition method. By partition method, we can tell easily how many Jordan block possible for this matrix with this characteristic polynomial and minimal polynomial. Let's see. Notice the characteristic polynomial since x plus 4 to the power 5 times x minus 1 whole cube. That means for the eigenvalue lambda equal to minus 4, the algebraic multiplicity is 5 and for lambda equal to 1, the algebraic multiplicity is 3. Means for lambda equal to minus 4, highest degree possible Jordan block would be 2. For lambda equal to minus 1, since minimal polynomial is x minus 1, that means geometric multiplicity for lambda equal to 1 is 1. Therefore, here highest possible Jordan block is only 1. Therefore, we can write corresponding to lambda equal to minus 4, 5 equal to, since for this highest possible Jordan block is 2, that means we can write this as 2 plus 1 plus 1 plus 1. Are you getting? Also, we can write this otherwise, or 5 equal to 2 plus, since highest possible Jordan block is 2, 2 plus 2 plus 1, and we can write 3 equal to 1 plus 1 plus 1. So, number of possible Jordan block is, since algebraic multiplicity for lambda equal to minus 4 is 5, therefore this would be minus 4, minus 4, minus 4, minus 4, minus 4, and since algebraic multiplicity of lambda equal to 1 is 3, that means here would be 1, 1, 1, and since if we consider this block, since here the 2 plus partition is 2 plus 1 plus 1, therefore that means here would be 1, here 0, 0, 1, 2, 3, 4, 0, 0, 0, 0. And here also 0, 0, 0, 0, 0. Here would be 0, 0, 0, 0, 0. Here also 0, 0. Here 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Here also 0. Here 0, 0, 0, 0, 0. Here 0, 0. 0, 0, 0, 0, 0, 0. Here also 0. Here also 0, 0, 0, 0, 0, 0, 0. Are you getting? And notice the degree of Jordan block is 2. And since the partition is 2 plus 1 plus 1, here degree of Jordan block is 1. 1. And for this 3 equal to 1 plus 1 plus 1. So here degree of Jordan block is 1. Okay? Are you getting the Jordan canonical from? Another way, consider this partition 5 equal to 2 plus 2 plus 1. Since here 5 equal to 2 plus 2 plus 1, that means for lambda equal to minus 4, there exists 2 Jordan block of order 2. And here also 3 equal to 1 plus 1 plus 1. That means here for lambda equal to 1, there exists 3 Jordan block of degree 1. Are you getting? Are you getting? By partition method, we can easily tell how many Jordan block exist. Okay. That means the possible number of Jordan canonical form is 2. See one question which had come CSR NET June 2018 exam. The question is, let A be a 6 cross 6 matrix over the field R with characteristic polynomial x minus 3 whole square times x minus 2 to the power 4, and the minimal polynomial is x minus 3 times x minus 2 whole square. Then what is the Jordan canonical form of the matrix A? Notice, here A is 6 cross 6 matrix over the field R. Since here the minimal polynomial is x minus 3 times x minus 2 whole square. That means, and the characteristic polynomial is x minus 3 whole square times x minus 2 to the power 4. Therefore, the eigenvalue of 3 with multiplicity am equal to 2 and eigenvalue of 2 with multiplicity am equal to 4. Okay? And notice, since here the minimal polynomial is x minus 3 times x minus 2 whole square, so obviously geometric multiplicity of lambda equal to 3 is 1 and geometric multiplicity of lambda equal to 2 is 2. And notice, since geometric multiplicity of lambda equal to 3 is 1, that means highest possibility of Jordan block is 1 for lambda equal to 3. And geometric multiplicity of lambda equal to 2 is since 2. The Jordan canonical form of A is, since here the algebraic multiplicity of 3 is 2, but highest possibility of Jordan block is 1. That means this block is possible. And here notice the order of Jordan block for lambda equal to 2 is 4. So this cannot possible, because for lambda equal to 2, the highest possible of Jordan block is 2. Now notice the second option. Here highest possibility of Jordan block is 1. Here 1. Sorry, here the order of Jordan block is 2. Here 1. Here 1. Okay. So this is possible because here the partition is for lambda equal to 2. Here the partition is 2 plus 1 plus 1. Okay. And let's see the option 3. Here the highest possible Jordan block since lambda equal to 3 is 1. Here also 1. Here highest possibility of Jordan block for lambda equal to 2 is since 2. And here notice this is Jordan block of order 2. This is also Jordan block of order 2. Okay. And this partition obviously possible because here 4 equal to 2 plus 2. Okay. And notice the fourth option. Here the order of the Jordan block for lambda equal to 3 is 2. So this is cannot possible. That means only option 2 and option 3 are right option. Are you getting? Oh well. I will see our next goal of this lecture. Generalized eigenvector. When there exists eigenvector of this matrix, we all of us know a v1 equal to lambda times v1. Actually this means a minus lambda times v1 equal to 0. But generalized eigenvector means this would be such type. A v1 equal to lambda v2 plus v1. Okay. What is the generalized eigenvector? I will see by an example. Consider this matrix and notice here the eigenvalue are 2, 2 and 2. Then if we want to find the eigenvector, obviously this would be a minus 2x would be 0 vector. That imply y plus z equal to 0 and z equal to 0. And since z equal to 0, that means obviously y equal to 0. So eigenvector is C00 type. Here notice rank of a minus 2i is 2 and nullity of a minus 2i is 1. That means geometric multiplicity here 1. That means only one linearly independent eigenvector exists and A is similar to this Jordan canonical form. And here notice this one and this one obviously represent two missing eigenvector. That means these would be x2 vector and x3 vector not be eigenvector. These vector x2 and x3 be the generalized eigenvector. Okay. And this is the idea of generalized eigenvector. Okay. Oh well. Now I will prove how x2 and x3 these two vectors are generalized eigenvector. For this a times x1 comma x2 comma x3 equal to, this is the matrix A times, this means x1 comma x2 comma x3, and from this equation we can tell since this vector is eigenvector, that means obviously a x1 equal to 2 times x1, and I will prove these two vector means x2 and x3 with the generalized eigenvector. Here notice obviously a x2 equal to obviously x1 plus 2x2. That means obviously a minus 2i times x2 equal to x1. Okay. So from this expression we can tell x2 not belongs to null space of a minus 2i. But here notice obviously x1 belongs to null space of a minus 2i because here this imply a minus 2i times x1 equal to 0. Okay. Now multiply this equation by a minus 2i. Then this would be a minus 2i whole square times x2 equal to a minus 2i times x1. Okay, and obviously a minus 2i times x1 means 0. So this is equal to 0. So from this expression we can tell x2 belongs to null space of a minus 2i whole square. That means obviously this vector x2 is nothing but this. This vector is generalized eigenvector. Are you getting? And the picture would be such type. This is the eigenspace null space of a minus 2i. And here the vector x1 belongs to, and this is the null space of a minus 2i whole square, and the vector x2 belongs to this null space. Now I will see x3 belongs to null space of a minus 2i whole cube. Similarly, I will get a x3 equal to x2 plus 2x3. That means from this line we can tell a minus 2i x3 equal to x2. Now multiply this equation by a minus 2i. Therefore, this means obviously a minus 2i whole square x3 equal to a minus 2i x2. And a minus 2i x2 equal to x1. That means a minus 2i x2 equal to x1. Now multiply this equation by both sides by a minus 2i. Then this would be a minus 2i whole cube x3 equal to a minus 2i x1. And obviously a minus 2i x1 means obviously this is 0. Means this value is equal to 0. That means I have got a minus 2i whole cube times x3 equal to 0. And from this expression obviously x3 belongs to null space of a minus 2i whole cube. That means x3 not belongs to null space of a minus 2i whole square, but x3 belongs to null space of a minus 2i whole cube. That means obviously this x3 belongs to null space of a minus 2i whole cube. Okay, are you getting the method? Well, now try to solve this generalized eigenvector own self. This is very easy. If you don't evaluate this generalized eigenvector by this method, please do comments in comments box. Obviously, I will solve this process in my next video. That means actual idea of generalized eigenvector is if A is n cross n matrix, then a generalized eigenvector of the matrix A corresponding to the eigenvalue lambda is a non-zero vector which is satisfying the equation a minus lambda I to the power px equal to 0, where for some integer p such that a minus lambda I to the power p minus x not equal to 0. That means the generalized eigenvector x belongs to null space of a minus lambda I to the power p. Are you getting? Therefore, since every n cross n matrix is similar to Jordan canonical form, then equal to Sj S inverse, where obviously S is the matrix containing eigenvector and generalized eigenvector of the matrix A. Are you getting? And when the matrix is diagonalizable, is equal to PDP inverse, where this P and P inverse contain only eigenvector, because for diagonalizable, every eigenvector are linearly independent. Are you getting? Today I will stop here. In my next video, I will discuss some question which had come different type of competitive exam. But at first I will highly recommend you please see today's video with pay attention, because this concept is very important for any competitive exam. See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel for more videos. Thank you so much.